Okay, so today we are discussing about the frame structure used in GSM. So actually, there should be a proper format that needs to be standardized so that the equipment manufactured by different companies can be able to understand it if they follow the same standard format. So each user will be transmitting according to the frame structure, okay, that is standardized. So user will be transmitting a burst of data, okay, within the time slot which is assigned for the user. So depending upon the kind of transmission, the type of transmission, a specific frame format is followed so that they will be able to understand what kind of information is being passed through. So because many kinds of information will be passed, you need to have specific frame format for each type of communication. So there are five specific frame format defined. One is the normal burst, okay, which is the normal data transmission, okay, which is used in traffic channels and DCCS transmissions on both the forward and reverse links. Now, FCCH channels and SCH bursts that are used on time slot 0, they need to use specific frame formats to broadcast the frequency and time synchronization of the network. So these synchronization messages are transmitted to other users in the network using the specific frame formats. RCH burst is used by all mobiles to access services from any base station. So sometimes you need to transmit, you need to keep idle. There's no data to transmit. In that case, you'll transmit dummy burst, okay, which has a specific format, okay, which is used as a filler information in those unused time slots. Instead of leaving the time slots unused, just left free, you will be transmitting dummy burst on the forward link. It has its own advantages. So these are the data bus used in GSM. So the normal bus consists of 3 start bits, 58 bits of encrypted data, 26 training bits, 58 bits of encrypted data, 3 stop bits, and the guard period. Next, FCCH bus consists of 3 start bits and 142 fixed bits of all zeros, 3 stop bits, and the guard period of 8.25 bits. SCH burst similarly consists of 3 start bits, 39 bits of encrypted data, 64 bits of training, 39 bits of encrypted data, 3 stop bits, and 8.25 bits of guard period. So RACH bus consists of 8 start bits, 41 bits of synchronization data, 36 bits of encrypted data, 3 stop bits, and we have appended to it an extended guard period of 68.25 bits. Okay, so the dummy bus where you send this on idle time slots will have the format with starting with 3 start bits, 58 mixed bits, 28 training bits followed by 58 mixed bits, 3 stop bits, and a guard period of 8.25 bits. The data structure within a normal bus consists of 148 bits, which are transmitted at a rate of 270.833 kilobits per second, and an unused guard time of 8.25 bits, which is provided at the end of each bus. Out of the total 148 bits per time slot, 114 are information bearing bits, which are transmitted as 257-bit sequences. 257-bit sequences close to the beginning and end of the burst. So the mid-amble consists of 28-bit training sequence, which allows the adaptive equalizer in the mobile or base station receiver to analyze the radio channel channel characteristics and before decoding of the user data. So these 28 training bits are used for equalization, okay, to compensate the channel effects. Okay, so that the receiver is tuned to the channel state, and based on the uh, channel state information, it will recover the bit sequence. On either side of the mid-amble, you have two control bits, all stealing flags. Now, these two flags are used to distinguish whether the time slot contains voice or control. Okay, both of them share the same physical channel. Now, during a frame, a GSM subscriber unit uses one time slot to transmit and one time slot to receive, and may use other 6 spare time slots to measure the. See, you should know that there are 8 time slots in the frame. So if it uses one time slot to transmit and one time slot for receive, it can monitor the next 6 time slots to measure the signal strength on 5 adjacent base stations as well as its own base station. So 5 adjacent, you have 6 time slots. Each time slot you use for a base station, one time slot for its own base station, and the rest of the 5 slots for the other neighboring base stations. So if you find the other base station signal is much better than the current base station, it may request for a handoff. Okay, so it will not do it immediately, but you should not make decisions too quickly. You should observe this over a period of time. Okay, after observing for a certain period, then only you make a decision whether you really require a handoff or not. Sometimes things are very temporary. So if you have I told you each frame consists of 8 time slots. These are the time slots from 0, 1, 2, 3, 4, 5, 6, 7. So 0 to 7 are the time slots. So you have 8 time slots. And the structure of each time slot is like this. You have 3 bits, 57 coded data, 1 steal bit. So these steal bits, I told you, they are used for use overriding the time slot with the control information. Okay, so 26 mid-amble bits, 21 stealing bits, 57 coded data, 3 bits, and 8.25 God period. So these frames, 26 of those frames will constitute a multi-frame, Okay, and such multi-frames, 51 of them forms a super frame. The super frame spans 6.12 seconds, whereas the multi-frame, which consists of 26 frames, constitutes 120 milliseconds. The frame duration is 4.615 milliseconds, which consists of 8 time slots. Each time slot is 576.92 microseconds. So these 8 time slots per TDMA frame, the frame period as mentioned will be 4.615 milliseconds. So you can transmit 1250 bits in that time frame, although some bit periods are not used. Frame rate is 270.833 kilobits per second or 120 bits per frame. Okay. Either if you look in terms of bit rate, it is 270.833 kilobits per second. Whereas you have, if you measure the time, that corresponds to 1250 bits per frame, or you have 216.66 frames per second. The 13th and 26th frame are not used for traffic but are used for control purposes. Each of the normal speech frames are grouped into larger structures and multi-frames, which in turn are grouped into superframes and hyperframes. The multi-frame consists of 26 TDMA frames and one superframe consists of 51 multi-frames or 1326 TDMA frames. A hyperframe consists of 2048 superframes, or that corresponds to, if you express that in terms of TDMA frames, it will be 2715648 TDMA frames. In GSM, a complete hyperframe is sent at about every 3 hours, 28 minutes, and 54 seconds. Now, this is important to GSM because encryption algorithms rely on a particular frame number, and you need to provide sufficient security, and it can be only obtained by using large number of frames as provided by the hyperframe. Now the control frames spans 51 frames, which is 235.365 milliseconds as opposed to 120 milliseconds of the traffic frame. Traffic or dedicated control channel multi-frame. So the control frame is uh, uh, larger in time, occupies larger time, occupies large time than compared to a traffic dedicated channel control multi-frame. Now, this is done intentionally to ensure that any GSM subscriber, whether he is in the serving cell or adjacent cell, will be certain to receive SCH and FCCH transmissions from the BCH. Okay, no matter what particular frame or time slot they are using. Now, coming to signal processing, we are basically concerned with transmitting speech because of GSM was originally developed for talking. Even the mobiles today, the main purpose is to talk to your friends or your colleagues over the phone. So the main service is speech service. So speech is the core service. Speech transmission is the core service. It is provided by a mobile phone. So we are looking at here how that is being transmitted from the source to until the destination. The speech is first digitized and you use source coding to remove any redundancy in the digitized speech signal. Then you do channel coding. Channel coding is quite the opposite. You add redundancy to overcome the channel effects. So then, in order to overcome fading, you use interleaving techniques. Okay. So then you format as a burst. Then you use after doing these things. All this has to do with the techniques necessary for transmission of the data. Digitizing, source coding, channel coding, interleaving, and burst formatting all has to do with the engineering techniques transmit the data to the other side. But we are uh, we have to protect our system from events dropping and all those things so that our conversations doesn't fall into the ears of some unintended people or some unintended persons. We need some kind of ciphering, yes, kind of to provide some kind of security, some kind of encryption. So after all the techniques used for transmitting the data to the other end, at the end you will pass it to a block called ciphering. Once the text is encrypted, passed to a ciphering block, you have to actually transmit. So transmit the data. So the output of the ciphering is also a sequence of zeros and ones, but zeros and ones cannot be transmitted directly. You need proper modulation depending upon the channel. So you pass it through the modulation block. Okay, you will pass it to modulation block, and after the modulation block, the corresponding signals, radio signals, are transmitted from the transmitter to the receiver. So at the receiver, you receive the signals. So you have to do demodulation. After you do the demodulation, you require zeros and ones, which is a scrambled uh, data, which is encrypted data. You need to decrypt it, which you basically decipher this. Okay, then you follow the reverse processing of what is used as techniques in while transmitting the uh, data, okay, or speech data, which is like you need to recover from the first formatting, then you have to de-interleave, then you do channel decoding and next source decoding, and you from source decoding you receive the speech. Now, speech coding. The speech coder is based on residually excited linear predictive coder RELP, which is which is enhanced by including long-term predictor. Okay, so you use RELP along with LTP. The coder provides 260 bits for each. You take 20 milliseconds of blocks of speech. Okay, so you divide your conversation into 20 milliseconds of speech each block. You convert that 20 milliseconds of speech, that sound, into 260 bits, which is which will correspond to 13 kilobits per second data. The speech decoder takes advantage of the fact of the normal conversation because we take advantage of the gaps in the conversation. So, if you take a normal conversation, each person speaks at an average of less than 40% of the time. So, there will be gaps between the sounds, okay, when he's speaking, and because alternatively there will be gaps. So, if you use a voice activity decoder, the speech coder, you can view this as a discontinuous transmission. So GSM will operate in discontinuous transmission mode, which provides a longer sustainable battery life. So if you want to transmit discontinuously, taking advantage of this information that you will not be able to talk continuously, so you can use this DTX mode to actually save battery life and reduce the instantaneous radio interference. Uh, okay, since the GSM transmitter is not active during the silence periods, so you can basically silence your transmitter during the silent periods. Now, because of the discontinuous transmission, you see a annoying noise coming. So to comfort that noise system at the receiving end, you induce a background acoustic noise to compensate this annoying switch muting noise. Mute, you have suddenly the sound comes and mutes sound and so these abrupt changes in the sound levels can be smoothed by the acoustic noise to compensate, which occurs during the DTX discontinuous transmission mode. Now, channel coding. Channel coding, which output bits of the speech coder are ordered in the groups, and to protect them from error. Okay, we use channel coding based upon the significance of in contributing to the switch quality. We use this. So what we do is, out of 260 bits in the frame, we group them. The most important 50 bits, what we do is we group them into three categories basically. First, the most important 50 bits. If those bits are lost, you cannot recover what is inside. So those most important 50 bits are called IA bits and have three parity check CRC added to them. So if these are lost, you cannot recover the conversation. Okay, so these are the most important bits called IA bits. So this facilitates this three parity check bits, CRC bits on those 50 bits facilitates the detection of non-correctable errors. You cannot correct them, but you can detect them at the receiver. The next 132 bits, along with the first three, first 53, because you see, the most important bits are 50 bits and three parity bits. Total is 50 plus 3, 53. So the next 132 bits, along with those 53 bits, 50 type IA bits and 3 parity bits are reordered and appended by 4 trailing 0 bits. 4 trailing 0 bits. Now, upon doing this, you will have a data block of 189 bits. This block is then encoded for error protection using 112 convolutional encoder with a constant length k is equal to 5. So if you pass through this encoder, you will get an output sequence of 378 bits. So the least important 78 bits do not have, so you have the least important 78 bits which do not have any error protection, and they are concatenated to the existing sequence to form a block of 456 bits in a uh, 20 milliseconds. 20 milliseconds. Yeah, 20 milliseconds frame. Yeah. So the error protection coding scheme increases the gross data rate of GSM with channel coding to now what was 13 kilobits per second data rate. Now you need to send at 22.8 kilobits per second because you are adding extra overhead. You are doing this. So this is how we can see in picture. See, these are the most important bits. Type 1A 50 bits, 1B type 1B are 132 bits. These are least important bits, 78 bits. So these are total 260 bits. If you add them, it will be 260 bits. These 260 bits we are dividing into three categories: type 1A, type 1B, and type 2. So this type 1A, you are appending three CRC bits to 50 bits. Then you are appending this 132 bits here with four trailing bits, 0 bits. Then this entire group is passed through half-rate convolutional coder with a constraint length of 52. So these bits are converted to 378 bits. 378 bits. So then this least important bits are just appended to this 378 bits. Okay. So a total of, if you add this bits to this bits, it will be all 456 bits for 20 milliseconds speech frame. So you will have, for every 20 milliseconds speech frame, okay, because we are taking 20 milliseconds of speech sound and converting it to 260 bits. That 260 bits have to be whatever bits that you uh, get after passing to the channel coding, that has to be transmitted within the same 20 milliseconds. Cannot extend that time beyond 20 milliseconds, because if you extend this beyond 20 milliseconds, when will you send the successive 20 milliseconds signal? So everything should happen within 20 milliseconds. So the channel coding for data channels. The coding provided for GSM full rate data channels is based on handling 60 bits of user data at 5 milliseconds interval. Okay, you do it according to a certain model standard, which is CCITTV.110. 240 bits of user data are applied to 4 trailing bits to a half-rate punctured convolutional coder with constraint length k is equal to 5. The resulting 488 coded bits are reduced to 456 bits encoded data bits through puncturing. We are using puncturing also. So puncturing means out of these 488 bits, coded bits, you won't transmit 32 bits. And the data is separated into four 114 bits data bursts that are applied in an interleaved fashion to the consecutive time slots. So the channel coding for control channels. GSM control channel messages are defined to be 184 bits long and are encoded using a shortened binary cyclic file code, followed by a half-rate convolutional coder. The file code uses the generator polynomial g5 of x is equal to x power 23 plus 1 times x power 17 plus x cube plus 1. If you multiply these two, you will get x power 40 plus x power 26 plus x power 23 plus x power 17 plus x power 3 plus 1. This produces 184 message bits followed by 40 parity bits. 4 tail bits are added to clear the convolutional coder which follows it, yielding a 228-bit data block. Now, interleave. In order to minimize the effect of sudden fades, like if you don't use interleaving, what happens is suddenly when a deep fade comes, all the data in that deep fade is lost. So you cannot recover. So in order to overcome that, you use interleaving. So, in order to minimize the effects of sudden fades on received data, a total of 456 encoded bits within each 20 milliframes message frame or a control message frame are broken into 857-bit subblocks. So you divide them into 87-bit subblocks. These 8 subblocks make up a single speech frame and they are separated spread over 8 consecutive TCS time slots. So instead of sending the entire block of 20 milliseconds in one time slot, you divide it into 8 time slots and you pass one part in one of the consecutive time slots. So 8 consecutive frames are needed. So if a burst is lost, if it happens that if the burst is lost due to interference or fading, channel coding ensures that enough bits will are still be received correctly to allow the error correction to work. So if you lose one of those blocks, you can still be able to recover. Each TCH time slot carries 257-bit blocks of data from two different 20 milliseconds, 456-bit speech or control segments. Now ciphering. It modifies the contents of the 8 interleaved blocks through the use of encryption techniques known only to the particular mobile station and base transceiver station. Now, it is further enhanced, security is further enhanced by the fact that encryption algorithm is changed from call to call. You will be changing the encryption algorithm from one call to other call. Two types of ciphering algorithms called A3 and AS are used in GSM to prevent unauthorized network access and privacy for the radio transmission respectively. The A3 algorithm is used to authenticate each mobile by verifying the user's passcode within the SIM and the cryptographic key at the MSC. The ACE algorithm provides the scrambling for the 114 coded data bits sent in each time slots. Now, bus formatting adds bus formatting adds binary data to the ciphered blocks in order to help synchronization and equalization of the received signal. Modulation is used by GSM, okay, to transmit the data zeros and ones. So 0.3 GMSK is used, where 0.3 describes the 3 dB bandwidth of Gaussian pulse shaping filter with relation to the bit rate. GMSK is a special type of digital modulation. Binary ones and zeros are represented in GSM by shifting the RF carrier by plus or minus 67.708 kilohertz. The channel data rate of GSM is 270.83333 kilobits per second, which is exactly 4 times the RF frequency shift. Now, this will minimize the bandwidth occupied by the modulation spectrum and hence improves the channel capacity. So, the MSK modulated signal is passed through Gaussian filter to smooth the rapid frequency transitions which would otherwise spread energy into adjacent channels. Frequency hopping. Under normal conditions, each data burst belonging to a particular physical channel is transmitted using the same carrier frequency. Okay, this is under normal conditions. However, if users in a particular cell have severe multipath problems, the cell may be defined as hopping cell by the network operator, in which case slow frequency hopping may be implemented to combat the multipath or interference effects in that cell. Now, frequency hopping is carried out frame by frame basis. The hopping occurs at a maximum rate of 217.6 hops per second. You will use as many as 64 different channels. Okay, use for hopping sequence, and it is repeated. The hopping sequence is repeated. So it is not a standard. It is completely specified by the service provider. The hopping sequence is completely specified by the service provider. Equalization is performed at the receiver with the help of training sequences transmitted in the mid-angle of every time slot. The type of equalizer for GSM is not specified and is left up to the manufacturer. So demodulation, the portion of the transmitted forward channel signal is which is of interest to a particular user is determined by the assigned time slot and ARFCN. The appropriate time slot is demodulated with the aid of synchronization data provided by the bus formatting. After demodulation, the binary information is deciphered, deinterleaved, channel decoded, and speech decoded. Okay, so we have finished this unit 3. Next class will be starting unit 4. Okay, all of you be ready to give the attendance. Quickly give the attendance. 35 plus 46. So 81 people has to give the attendance. Come on, quick. The link will be disabled very quickly. Okay, all of you did that. Anybody left? Okay, thank you.